Electrical grounding is a critical aspect of electrical safety and system functionality. It provides a low-impedance path for fault current to return to the source, facilitating the operation of overcurrent protection devices like circuit breakers and fuses. Without proper grounding, fault currents can persist, creating dangerous conditions and increasing the risk of electrical shock, fire, and equipment damage. The main purpose of grounding is to limit the voltage on equipment enclosures and conductive parts to safe levels during a fault condition. This is achieved by connecting these parts to ground, which provides a return path for fault current. When a fault occurs, the current flows through the grounding system back to the source, causing the overcurrent protection device to trip and de-energize the circuit. Grounding systems typically consist of a grounding electrode, such as a ground rod or a metallic water pipe, connected to the earth. The grounding electrode provides a connection to the earth, which serves as a reference point for voltage. The grounding electrode conductor connects the grounding electrode to the equipment grounding bus in the electrical panel. The equipment grounding conductor provides a path for fault current to return to the source from equipment enclosures and conductive parts. Grounding and bonding are related but distinct concepts. Grounding refers to connecting electrical systems and equipment to the earth, while bonding refers to connecting different metallic parts together to create a continuous electrical path. Bonding is essential for minimizing voltage differences between metallic parts, which can prevent electrical shock hazards. The National Electrical Code, (NEC), provides comprehensive requirements for grounding and bonding in electrical systems. These requirements are designed to ensure electrical safety and prevent electrical hazards. The NEC covers various aspects of grounding, including the size and type of grounding conductors, the installation of grounding electrodes, and the bonding of metallic parts. Understanding the different types of grounding systems is important for electrical professionals. The most common types of grounding systems include solidly grounded systems, impedance grounded systems, and ungrounded systems. Solidly grounded systems have a direct connection between the neutral point of the transformer or generator and ground. Impedance grounded systems use an impedance, such as a resistor, in the grounding path to limit the fault current. Ungrounded systems do not have a direct connection to ground, but they may have a high impedance connection to ground. Each type of grounding system has its own advantages and disadvantages, and the selection of the appropriate grounding system depends on the specific application and requirements. Ground fault circuit interrupters, or GFCIs, are important safety devices that protect people from electrical shock. GFCIs monitor the current flowing in the hot and neutral conductors of a circuit. If there is a difference of 5 mA or more between the currents, the GFCI trips and interrupts the circuit. GFCIs are commonly used in areas where there is a risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. Regular testing of GFCIs is essential to ensure that they are functioning properly. Surge protection devices, or SPDs, protect electrical equipment from voltage surges caused by lightning, power outages, and other events. SPD diverts surge current to ground, preventing it from damaging sensitive electronic equipment. SPD are typically installed at the service entrance of a building or at individual equipment locations. Proper grounding is essential for the effective operation of SPD. Grounding conductors must be sized according to the requirements of the NEC. The size of the grounding conductor depends on the size of the overcurrent protection device protecting the circuit. The NEC provides tables that specify the minimum size of grounding conductors for different circuit sizes. Grounding conductors must be made of copper or other approved materials. Grounding connections must be made using approved methods and connectors. Grounding electrodes must be installed in accordance with the requirements of the NEC. The type and number of grounding electrodes required depends on the soil conditions and the size of the electrical system. Grounding electrodes must be installed below the frost line to prevent damage from freezing and thawing. The resistance of the grounding system must be low enough to ensure that fault currents can flow back to the source. The NEC specifies the maximum allowable resistance for grounding systems. Ground resistance testing is performed to verify that the grounding system meets the requirements of the NEC. Ground resistance testers are used to measure the resistance of the grounding system. The fall-off potential method is a common method for measuring ground resistance. Bonding jumpers are used to connect different metallic parts together to create a continuous electrical path. Bonding jumpers must be sized according to the requirements of the NEC. Bonding jumpers must be made of copper or other approved materials. Bonding connections must be made using approved methods and connectors. Equipment grounding conductors provide a path for fault current to return to the source from equipment enclosures and conductive parts. Equipment grounding conductors must be sized according to the requirements of the NEC. Equipment grounding conductors must be made of copper or other approved materials. Equipment grounding conductors must be installed in the same raceway or cable as the circuit conductors. Neutral conductors carry the normal unbalanced current in a 3-wire or 4-wire electrical system. Neutral conductors must be sized according to the requirements of the NEC. Neutral conductors must be insulated. Neutral conductors must be connected to the neutral bus in the electrical panel. The neutral bus must be bonded to the grounding bus in the electrical panel. Grounding and bonding are essential for electrical safety and system functionality. Proper grounding and bonding practices can prevent electrical shock hazards, fire hazards, and equipment damage. The NEC provides comprehensive requirements for grounding and bonding in electrical systems. Understanding the requirements of the NEC and following proper grounding and bonding practices is essential for electrical professionals. Common grounding mistakes can compromise electrical safety. Some of these mistakes are improper sizing of grounding conductors, inadequate bonding of metallic parts, failure to install grounding electrodes properly, and neglecting to test ground resistance. Avoiding these mistakes is crucial for ensuring a safe and reliable electrical system. Grounding systems should be inspected and tested regularly to ensure that they are functioning properly. Visual inspections can identify any signs of damage or corrosion. Ground resistance testing can verify that the grounding system meets the requirements of the NEC. Regular maintenance of grounding systems can prevent electrical hazards and ensure the long-term reliability of the electrical system. Grounding and lightning protection are two different but related concepts. Grounding provides a path for fault current to return to the source, while lightning protection protects buildings and equipment from lightning strikes. Lightning protection systems typically consist of lightning rods, grounding conductors, and surge protection devices. Proper grounding is essential for the effective operation of lightning protection systems. In summary, electrical grounding is a fundamental aspect of electrical safety. It ensures that fault currents are safely conducted back to the source, preventing dangerous voltage buildup and facilitating the operation of overcurrent protection devices. Understanding grounding principles, adhering to NEC requirements, and implementing proper grounding practices are essential for all electrical professionals and anyone working with electrical systems. This includes proper selection and installation of grounding conductors, electrodes, and bonding jumpers. Regular inspection and testing of grounding systems are also crucial for maintaining their effectiveness and ensuring long-term safety. Grounding provides a low-impedance path for fault current, limiting voltage on enclosures during faults and enabling overcurrent devices to trip. Grounding electrodes, such as rods or water pipes, connect to the earth, providing a reference point. The equipment grounding conductor connects enclosures to the grounding bus. Bonding connects metallic parts to minimize voltage differences. The National Electrical Code, or NEC, provides grounding requirements. Common grounding systems include solidly grounded, impedance grounded, and ungrounded. Ground fault circuit interrupters, or GFCIs, protect against electrical shock. Surge protection devices, or SPDs, protect equipment from voltage surges. Grounding conductors must be sized according to NEC tables, using copper or approved materials and methods. Ground resistance testing verifies the system meets NEC requirements, using methods like the fall-off potential. Bonding jumpers connect metallic parts, sized per the NEC. Equipment grounding conductors provide a fault current path. Neutral conductors carry unbalanced current and connect to the neutral bus, which is bonded to the grounding bus. Grounding mistakes include improper sizing, inadequate bonding, and poor electrode installation. Regular inspection and testing are crucial. Lightning protection systems use lightning rods, grounding conductors, and surge protection devices, requiring proper grounding for effectiveness. Electrical codes and standards such as the NEC are updated regularly to reflect new technologies and best practices. Staying current with these codes and standards is essential for electrical professionals. Continued education and training are also important for maintaining competency in grounding and bonding techniques.